Good morning and welcome to the fourth office hours of Alien Worlds here in summer of 2015. I'm here with Aurora again, and we're here to answer a bunch of questions. Many of you have posted questions on the discussion forum, and we'll look for your questions live as we are talking here. I hope that all of you have had an opportunity to look at some of the results from the Pluto mission from New Horizons. It's been pretty spectacular. Just the few images that we've seen so far have shown some amazing things on the surface of Pluto and its largest satellite, Charon, and actually even some of the other satellites in the Pluto system. So really, really exciting data, and over the next week or so, even more will come. And certainly Aurora and I are planning on shooting the epilogue for this course. So kind of an update of all the new material, and certainly we'll do a lot on Pluto. We're going to shoot that next week. So I guess without further ado, let's start the questions.
All right, so I don't know if I can hear it today. So the first question from the discussion forum is from Atoli, and it says, I need clarification on the Doppler shift details for the RV method. For the solar system, Jupiter is provided about 13 meters per second net movement of the sun. However, the sun is rotating rapidly, so that each limb is rotating both towards and away from the observer at around 2,000 meters per second at the equator. Doesn't this rotation affect the appearance of the Doppler shifts smeared out, or at least make the true RV Doppler shift harder to measure? Am I missing something obvious that makes this question moot?
Oh, that's a great question. So the question really is referring to, when we're observing the Doppler shift for the radial velocity method, we're looking as spectral features shift back and forth. So they shift to the red word when the object is going away from you, and they shift to the blue word when the object is coming towards you. If the star itself is rotating, this is what the person is asking, then one side of the star is actually going to be coming towards you, and the other one's going to be coming away from you. And that will actually broaden out the features. So it turns out that that is probably, does have an effect for the fastest rotating stars. A star like our sun actually isn't rotating very fast. It's actually a very slowly rotating star. Our star takes 28 days roughly to go once around, but there are stars like our sun that are fast rotators that take a day to do that. So our star is actually quite slow in comparison to other stars, and actually the effect of that broadening on the features is actually very minimal for a star like our sun. So it will broaden the features a little bit, but we'll still be able to see them shift left and right with pretty high precision.
All right, so the next question from the discussion forum says, can you talk a bit more about how one would interpret RV data for multiple planets?
Oh, yeah.
Is it similar to transit data, or are there different problems in the analysis to tease out the orbits for multiple planets?
Oh, that's great. So if you have multiple planets around a star for the radial velocity method, then you have kind of two wobbles at the same time. Well, when I'm in class, I don't know if I can do it here. I always say it's like wobbling. Let's see if you can see me. Here, I'll move my computer back. So, if you're orbiting and you do this, I'm wobbling, I'm the star, and so I'm coming towards you, and then away from you, and towards you, and away from you, right? And now if I add, there's one planet, let's say, orbiting me. But now if I have a second planet, in addition to this wobble of me going like this, I'm actually going to do a second wobble like this. So there's a wobble on top of a wobble. So what you end up measuring, and here I actually have something to write on, you write, if I have one planet, I might see a signal that looks something like this, where if this is time, and this is the radial velocity, so there you go. This is the radial velocity on the vertical axis and time on the horizontal axis. You would see something, the star going away from you, and then towards you, and away from you, and then towards you. But if I had a second planet, it might look something like this, where again, I have the bulk of the motion coming, oops, let me put it up here, the bulk of the motion coming away from you and then towards you, away from you and then towards you. But if you look, there's another signal on top of it. And that's a smaller planet in this case, or a closer planet because it has a shorter period. That's actually also going towards you, away from you, towards you, away from you, towards you, away from you, towards you, away from you on top of that signal. So what you actually get is signals superimposed on other signals. And this one's a kind of easy one to see, but actually a lot of the time it's very hard to see. And so you actually have to do some fancy kind of mathematical methods and modeling in order to pull out multiple signals from a radial velocity diagram. So it is similar into a transit in that the curve can contain multiple pieces of information, but it's different in that all of the wobbles are superimposed on each other. So the star is actually wobbling, feeling all of the different wobbles from all of the planets at once. So it's a little bit of a different way, but this kind of hopefully illustrates at least an easier case of that.
All right, the next question says, the advantage of the RV method compared to the transit method is that the orientation of the orbital plane is much relaxed, so that a Kepler-type mission using RV theoretically could provide a better estimate of the number of planets in the habitable zone of stars. Can you explain the RV versus transit methods in terms of sensitivity in the context of finding and cataloging exoplanets?
Awesome question. Yeah. So just so everyone understands, of course, for the transit method, you have to be, perfectly what we would say edge on. The star, remember, the planet has to pass perfectly in front of the star. You have to have perfect alignment between the star, the planet, and us here on Earth. For the radial velocity method, you can actually have some play. Like the star will still wobble a little bit towards you if the angle of if the orbit is a little bit angled towards us, so that we are actually sensitive to a wider range of orbital inclinations than we were with the transit method. The problem is that to take really, really high resolution spectra, which is what you need to actually be able to measure the Doppler motions down to a meter per second, or maybe even few tens of centimeters per second, which is the best we can do kind of right now, requires very, very high resolution instruments that take all of the light of the star and split it out into many, many components. And so if we want to then have enough light at all those different components, we can only really look at the brightest stars. And so the sensitivity is actually, I guess, much lower for the radial velocity method. And so we can't actually look at as many stars. Whereas for the transit method, something like Kepler can actually stare at the same patch of sky just over and over and literally look at hundreds of thousands of stars at exactly the same time with high enough precision to detect planets if they happen to pass in front. And it's usually we think about a 1 in 100, like a 1% chance that roughly that the planet's going to pass in front of the stars, maybe a few percent, but it's a very low percentage that you get that. But if you've got 100,000 objects to look at, now you're actually having some decent statistics. But you're exactly right. Hypothetically, if we had perfect instruments that could collect all the light from the star, we'd probably want to use the radial velocity method. But we don't have that technology yet. And we don't have telescopes that are big enough to collect enough light on a wide range of stars. And so the transit method really ends up still being the best way to identify exoplanets, even though it's missing all of the ones that are inclined to us a little bit.
Are there efforts to increase the technology for radial velocity telescopes?
Yeah, so we saw in the radial velocity method, we saw Professor Deborah Fisher down at Yale, who is building an instrument, and we actually went to her lab. Hopefully you all saw that in the interview. So she's one of the leading people, and there's other teams like her that are working on building better instruments that will be both higher precision, so they'll get down to smaller radial velocities, but also will have a high enough throughput so that you'll be able to see more stars. But I think transit method always is probably going to be the best way to do it, to at least identify worlds. Even though, again, you're missing probably a large fraction of them because they're not perfectly edge-on. Cool.
All right, so the next question from the discussion forum says, some 20 years ago, Earth-based radar suggested that there might be water-based ice on Mercury's North Pole. This was confirmed by MESSENGER probe in 2014 when water-based ice was found in craters at the North Pole. The tilt of Mercury is only some 2 degrees, which means that sub-zero temperature in areas shielded from the sun can quite happily cohabit with other areas at high temperatures. Since this fact seems to expand the limits of the Goldilocks zone, is a tilt a factor taken into account when looking for exoplanets?
Oh, that's an interesting question. Tilt probably is, so we usually don't talk much about tilt in general when we're thinking about exoplanets. It's very hard to measure for an exoplanet because we actually don't detect their rotation at all. That's maybe not true for all of them, but for most of the exoplanets, we get no information really about the tilt. Some people have thought about the tilt in terms of, it's of course what controls our seasons here on Earth, and so some people have thought having a stable tilt actually might be beneficial to things like life, because if you're constantly changing your tilt, then you're constantly changing your climate and your seasons, and it's maybe hard for life to set up. We don't really know if that's true for sure. And of course, our moon, it's actually gravitation and tidal force actually keeps our tilt very stable. That said, going back to the question, which was about the ice on the poles of Mercury, that even though Mercury is very close to the sun, there are places actually within impact craters near the poles of Mercury that actually are kind of in constant shadow. And so you can actually get water ice that stays there. Formally, that still doesn't make those worlds what we call habitable, because the true definition of a habitable world is actually having, at least as astronomers use it, is having the ability to have liquid water on the surface. And so that's frozen water on the surface. It doesn't mean necessarily just because a world doesn't have liquid water on the surface that it's really not habitable in the kind of just general sense of the word. You can imagine a world that has a frozen surface but a liquid interior or something that might be habitable. But having just ice on the poles, even for a hot world like Mercury, doesn't quite necessarily make it habitable. You really need it in probably liquid form to be useful. It's certainly interesting because it's a place you could go get water if you needed it. We find the same thing on the moon, actually. The moon, which really shouldn't have much water because it doesn't have the atmosphere to kind of sustain the water balance. It doesn't have much water, but it does actually have some water ice also in craters that are in constant shadow. So we see that there. And Mars, actually, although most of the polar ice caps on Mars are carbon dioxide, there is some actually water ice on Mars as well. At least it's been seen a little bit, and some people think there might be a larger amount, maybe some surface, something we will likely find with future Mars missions.
All right, so the next question says, a complicating factor for the habitable zone is the changing luminosity of the star. As M dwarfs evolve more slowly, do their hypothetical habitable zones stay more stable over time in terms of distance to the star than larger and hotter G-type stars like our sun? It's
a great question, kind of related to this week's material when we're talking about other stars. So all stars get hotter a little bit as they age. And it's a really, really cool thing that happens. It has to do with the fusion at the center of the star. By converting hydrogen into helium, you're actually reducing the number of particles in the sun or the star. And so the star actually doesn't then have as many particles to hold it upright, because it needs all of that pressure of the different particles kind of bouncing around and pushing back. And so to actually respond to that, to keep itself roughly the same size, what it does is actually gets hotter, which actually then gives it enough pressure to overcome the force of gravity. And so a star like our sun is actually about 30% hotter today than it was when it started. And so over the course of 4.5 billion years, the sun has gotten hotter, and it will continue to get hotter. In fact, the sun will actually get so hot in a while from now, in a long while from now, where it will actually begin to start boiling off the oceans, and we'll actually probably have total cloud cover on the surface of the Earth just because of the hotter sun. So certainly, like, that does play a role. As stars age, the habitable zone moves outward. But as the question indicated, the smaller stars evolve much slower. So the lifetime of, say, an M dwarf is somewhere from 100 billion years to over 1 trillion years. And it's going to increase, a bit over that 1 trillion years. But in the span of at least the age of our solar system, 5-ish, even to 10 billion years, an M dwarf hasn't changed at all. So over the course of the age of the universe, now about 14 billion years, the luminosity of the tiniest stars hasn't changed at all. And so their habitable zones are very constant. So yes, that is something we certainly think about. It means that planets that are maybe outside of the habitable zone when the system forms may become habitable around, say, a star like the sun. So yeah, we certainly think about that when we're detecting planets and trying to understand if they are indeed habitable, or will be, or were.
We may have to move to Mars.
That's right. Mars will be habitable at some point. Only problem is it's, of course, just not, has just too little gravity to really hold on to enough atmosphere. So unless we can find out a way to kind of constantly pump atmosphere in, like we talked about in a previous office hours, probably Mars is going to be a hard place to live anytime soon, at least.
Is Earth going to look something like Venus, do you think?
Oh, so Aurora asked if Earth was going to look like Venus. Venus is pretty extreme. Earth will certainly probably be totally cloud covered at some point. So it'll be like Venus in that way. Like, you won't be able to see the surface. It'll actually be dark on the surface. It's a little depressing. When that happens, probably photosynthesis ends, which actually probably means the end of most life on Earth, because all the food chains will break down. There probably will be some water life that survives, but most land life will die at that point. It's uplifting. But probably Earth will never get the surface pressures, the immense surface pressures that Venus has, just because Earth still will probably have mechanisms for recycling things like CO2. Our CO2 gets captured by weathering and actually gets stored in the Earth from plate subduction. And so we actually have some mechanisms for like controlling some of the amounts of the CO2, things like CO2 in the atmosphere a little bit. And probably won't get as hot either. I mean, it will probably get very hot, but probably not as hot as Venus. But, it will be a totally cloud-covered, dark, depressing, at least surface, lifeless world. Wow.
Good things to look forward to.
Yeah, good things to look forward to someday, a long time from now, when we're all gone.
So actually, the next question is related.
Oh, okay.
It says, greenhouse gases are a factor for keeping water liquid on a planetary surface. As our sun gets hotter, the CO2 in our atmosphere must be reduced to keep the surface temperature stable. Can you talk a little bit about different gases that are needed at various stages of terrestrial planetary evolution to maintain a habitable surface during the evolution of its star?
Oh, wow. So, the gases that are really important are the greenhouse gases. CO2 is the one that we hear a lot about in the news and whatnot because it's one that humans are outputting a lot of. So it's one where the kind of balance has been made out of whack by humans. But things like water is actually also a very strong greenhouse gas. And it's actually a stronger greenhouse gas than CO2 is, but it's not, there's the amount of water in the system isn't changing a lot on the Earth. We lose a little, we gain a little, but it's not something like humans are putting more into the atmosphere or things like that. So greenhouse gases, of course, are important because they do help regulate the temperature. Both they allow for a world to maybe be a little bit warmer than it should be. Earth is actually like that. If you look where Earth is around the sun, we actually should be much colder every day here on Earth, but we're actually kept warmer because of greenhouse gases. So a little bit of greenhouse gas is actually a really good thing. It's when you have too many that you get all sorts of problems. So you might want a little bit of greenhouse. It also keeps the world kind of a nice temperature, kind of almost everywhere on the world, even though like it can be colder in some regions and warmer and little. In the grand scheme of temperature fluctuations we see in even the solar system, the Earth is very stable. And some of that is the greenhouse gases and things like water in the atmosphere, which actually it's hard to change the temperature of water. And so it keeps things much more stable. The other components of our atmosphere, nitrogen is the biggest component, doesn't play a giant role besides just helping maintain the surface pressure on Earth. And of course, the oxygen that's vital to us as humans almost primarily comes from life on Earth. So although that's not an essential piece of kind of building a planet, certainly for human life and many of the animal life, the oxygen in the atmosphere is very key, which comes mostly from plants, things like algae. We have a lot of CO2 coming from other types of life on the Earth. And so that's a key signature of life if we were to see that on another world. Did I answer that? All right.
So?
Yeah, okay. If not, someone can write in another question.
Yeah. So the next question from the discussion section says, in watching a lecture and interview for Module 7, I was wondering, so there's 3 questions. I'll just read the first one first. Are there fewer O stars in the Milky Way because the Milky Way is older and the result of the early O stars to form the smaller stars in the galaxy and their planets, making them fewer in existence now, or have there always been fewer O stars?
Good question. Cool. So, of course, this question is about really trying to understand how many stars get formed when stars are born. And since we know that stars live different ages, you could make a guess that maybe we don't see as many of the big massive stars right now because they don't live very long. So they are born, they die, and then boom. Well, it turns out that is part of the reason. So part of the reason that O stars and B stars are so rare is that they're just really, really short-lived. So within the nearby-ish 30 light years or so from the sun, there are no O and B stars. That said, when you actually make stars, when you have a big burst of star formation, you still don't make very many O stars. How many do you know offhand, Aurora? How many like M stars you make per O star, roughly?
I think it's like 200 M stars to like 0.01 O stars.
Okay, so I don't know if you heard that, but she said for every 10th or 100th of an O star, so a fractional O star, you get a couple hundred M stars. So that would be for every 1 O star, you get something like 2,000 to 20,000 M stars. Wow. So they just start very, very rare. But then that's, of course, amplified, like the student asked in the question, by the fact that the M stars basically live forever, for all intensive purposes. But the O stars are very short-lived. They live, 1 million years, which in the grand scheme, again, of the universe is instantly.
So the next question is related, and it says, now that we can explore other galaxies, are we finding the same patterns of star-type frequencies, at least in the neighboring galaxies?
Yeah, that's awesome. So the question is about, do we see the same pattern of types of stars in other galaxies? And this is actually the research question that Aurora is working on right now. And the conference that we were attending in Baltimore a couple weeks ago was all about this question, called the initial mass function, like how many stars you get as a function of their mass. So how many low mass stars versus high mass stars do you get when stars form? And there is increasing evidence that it is not the same in other galaxies. So in our galaxy, it actually looks really similar. When we look in different places and different environments, there's a lot of evidence that shows that it looks pretty similar. You get about the same number of low mass stars as you do high mass stars. But in some other galaxies that aren't too far away, again, in the grand scheme of the universe, it does appear that in especially like big elliptical type galaxies, which we haven't talked a lot about in this class, but some of the biggest types of galaxies in the universe, you actually get even more of the lowest mass stars. And then there are some of the closest galaxies to us are these things called the ultra faint galaxies. They consist of just a handful of stars sometimes, but they're actually true galaxies. And those actually look like they have slightly different patterns in terms of how many stars they manufacture as a function of mass. So it does appear that there are some differences in galaxies, and maybe Aurora's research in a few years will tell us more. Great question.
Yeah. So the last question says, in the interview, Dr. Johnson mentioned the chemical composition of stars. Is it ever other than hydrogen and helium with their byproducts extending towards the heavier elements as the star ages?
I'm not sure I understand the question.
I think it's just asking about the chemical composition of stars, like what
the
highest elements.
Oh, okay. Yeah, so when we look at the chemical composition of stars, for the most part, we're looking at the material from which the star formed. So when stars are all on that main sequence that we talked about in the lecture, they're all turning hydrogen into helium. They're not doing anything else. They're not turning helium into carbon or oxygen. All of that happens when the star becomes a red giant. So it's actually kind of dying or in its way out, if you will. So on the main sequence, all stars are just turning things from hydrogen into helium. And so if we see other chemicals, other elements in their atmospheres, then we're actually seeing the material from which the stars formed. And we see a bunch of different things. We see iron, we see magnesium, we see oxygen. Some of that is the just types of enrichment that the galaxy went through as those massive stars formed higher elements and then exploded and sent the material out into the galaxy, and new stars formed from that. Some of it is actually the temperature of the stars. So at different temperatures, you can actually see different chemical signatures. Some of that has to do with the spectroscopy that we talked about. Remember me jumping up and down on the blocks. Those transitions are also, they're not just chemical dependent and light dependent, they're actually temperature dependent, it turns out, a little bit too. And so some of them are easier to see at different temperatures. So I study the very lowest mass stars, and a lot of what we see when we take a spectrum of, say, an M dwarf, is that we actually see molecules. We can see things like titanium oxide, calcium hydride. We can actually see water in some of the lowest mass stars, things like methane, carbon dioxide. So we see a lot of, although we see some atomic lines of set single elements, we actually see a lot of molecules, so multiple elements that have combined. that's just because it's so cool, or it's cooler in the atmosphere. It's not cold. It's still a star. But it's so much cooler that like the elements can combine to form molecules. So there's some temperature dependence too of which exact elements that we see. So what we have to do is put the types of elements that we see and how much of we see of them into models that try to model what the overall chemical composition would be of that star to actually see the features that we see. And that's some of what Professor Johnson was talking about. And one of the things that we have noticed is that it looks like in general planets are more common around stars that have more of these enriched, heavier elements. And that kind of should make sense, because to make a planet certainly like the Earth, or even a big planet like Jupiter, you need things like oxygen and iron and silicon and some of those things to build kind of the rocky or even icy base that will then make either an Earth, or will actually have enough gravity to hold on to the atmosphere of a world like Jupiter or Saturn. So I think that got that. Yeah.
Mm-hmm. Yeah, I mean, also I think in the red giant branch, you're burning other things besides hydrogen, helium.
Yeah, that's right. Yeah, so as soon as you get to the red giants, now you start making. So as soon as you turn into the red giant, now is when stars can make. They can make oxygen, they can make carbon, they can make silicon, they can make all the elements, actually up to iron. So iron's kind of the last element that you can make through fusion. All the other elements on the periodic table get made through other mechanisms, where you usually, one of the common ways is you actually inject neutrons into the nuclei of the atoms. And that one way that happens is actually in supernova explosions. So if you're wearing gold or silver jewelry, a lot of those were actually formed when you had an exploded star, and the neutrons get injected into the atoms, and you can actually make heavier elements, things like gold, silver, some of those heavier ones.
So I'm going to jump over to a question from the Google Hangout. It says, in recent years, there have been stellar classifications for stars even smaller than M-type, specifically L, T, and Y types. But where is the cutoff for considering these objects really small stars, and when are they just really large planets?
It's an awesome question, and at least I can see that it's from our former TA for the class, Brandon Harrison. So hi, Brandon. Thanks for the great question. So yeah, we talked about all these different types of stars, where M stars, and then L, and then there's actually T, and then Y. And the first Y dwarf was actually discovered by a Boston University alum. So the T and Y dwarfs are actually objects called brown dwarfs, and some of the L dwarfs too actually are as well. But all the T and Y dwarfs are objects called brown dwarfs, which are failed stars. They don't have enough mass to actually start fusing hydrogen into helium. You need roughly about 10 million Kelvin at the center of the star to start fusing hydrogen, to actually get those particles moving fast enough to smash together. It has to be about 10 million Kelvin. And so what happens is, as the star collapses, its gravity is pulling it closer and closer, and that's heating it up. And the more mass it has, the hotter the center will get. You actually start moving and pushing the particles around a lot more as the star collapses. And so once you get below roughly about 8/100ths, that's about right, 8/100ths of the mass of the sun, 0.08 of the mass of the sun, you can no longer start fusing hydrogen into helium. So that's the boundary where you no longer are a star. Below 0.08 times the mass of the sun, you basically aren't a star anymore. You are what's called a brown dwarf. But Brandon is asking, so if you keep going down, you get to cooler and cooler, smaller objects, and you start getting to where the line between a big planet, like a big Jupiter-sized planet, or bigger, or a small brown dwarf, gets kind of blurred. And there's actually been a bit of a debate in astronomy about this. Most people use a definition where they say that roughly the boundary is at 12 to 13 times the mass of Jupiter. That's what people use, that everything below that mass, about 12 to 13 times the mass of Jupiter, is considered a planet, and above that is a brown dwarf until you get to the stellar boundary. That number is not arbitrary. It's actually chosen because it turns out hydrogen and most of the elements come in different flavors. You can actually have all the elements are defined by the number of protons they have in them. So hydrogen has 1 proton. Most of the hydrogen that we encounter has 1 proton and no neutrons. But if you actually add a neutron to a hydrogen atom, it's still hydrogen, but it's what we call an isotope of hydrogen. And it's called, in that case, it actually has a name. It's called deuterium. And it turns out deuterium, because it's a little bit more massive, actually can fuse with other deuterium atoms at actually a slightly lower temperature. And so it turns out that actually you can go all the way down to about 12 to 13 times the mass of Jupiter, and you can actually get deuterium fusion. And so that is a physical limit that's been put that kind of defines the difference between a brown dwarf and a planet. And it means that brown dwarfs actually have a little bit of fusion, because there's a little bit of deuterium, but it doesn't last very long, and it doesn't really give them a whole lot of heat. And so that does happen, and it's the difference really between what we would classically call a brown dwarf or a planet. Now, where the debate comes is that you could imagine you could form something that's greater than 12 to 13 Jupiter masses around a star, right, in the disk of a star. And then is that just a really big planet? And maybe you can form something that's smaller than 12 to 13 Jupiter masses just through collapse of gas in a cloud, just like stars and most of the brown dwarfs form. And so is that really just a small brown dwarf? And so there's some people who debate that maybe we should use, instead of this mass definition, maybe we should use a formation definition. If it's forming in a disk, then maybe it's just a really, really big planet. And if it's forming like a star, maybe it's just a really, really, really small brown dwarf. The problem, of course, is it's often hard when we just see an object out in space to know whether it formed like a planet in a disk or collapsed from a disk like a star does. And so for right now, most people use the mass definition because that's kind of cleaner. And it's, again, doesn't come from an arbitrary place. So hope that answers your question, Brandon. Thanks for asking.
Do you think you could ever have a habitable planet around a brown dwarf?
Ooh, cool question. Yeah, you could have a habitable planet around a brown dwarf. You know, one of the problems with brown dwarfs is because they don't really have their a constant fusion source. They are giving off heat, but it's actually them just kind of cooling down. It's actually them probably finishing collapsing and re-radiating that heat out into space. But there probably is some kind of perfect zone where you could form a planet around a brown dwarf, and for a certain number of years, it would be habitable. And so you could imagine having the conditions just right to like set up even maybe life for a little bit on a brown dwarf. The problem is, of course, it would then get cold after a while because the brown dwarf would lose its heat. So unless you had a civilization that could, I don't know, advance and evolve very quickly and then move into a closer planet, kind of at the same rate that the brown dwarf is cooling, then you'd be in trouble.
All right, I'm going to go back to the discussion forum. So this is a kind of long intro.
Okay.
So it says, it is thought that with current observational techniques, Earth-like habitable zone rocky planets are likely to be found around M-dwarf stars. However, these stars are often also typically highly active magnetically, and they emit a large portion of their luminosity at UV, EUV, and X-ray wavelengths than other spectral types. To survive stellar stripping or evaporation of their atmosphere, planets may need to have strong magnetic fields and or thick Venus-like atmospheres to defend against radiation, the stellar wind, and coronal mass ejections. It has been hypothesized that the magneto-hydrodynamic interactions can also lead to significant Joule heating of their upper atmospheres. These considerations may greatly affect our interpretation of what constitutes the habitable zone in such systems. Do you agree?
Huh. So I don't know if everyone heard that, but I'll give a quick summary that basically, you know, around M dwarfs, you know, which we have said and seen that there are probably an abundant number of small rocky worlds, we may have to think a little bit more about this word habitability, which again, in the just really basic sense means, you know, the right distance to have liquid water on the surface. But as the student indicates, stars like M dwarfs actually stay very, what we call magnetically active for a long time. It's actually one of the research areas that I work on. And because they're magnetically active for sometimes many, many billions of years, that means they have large flares, really high energy emission that can bombard the planets, can actually strip away the atmosphere, can create extra heating in the atmosphere, can actually cause probably all sorts of problems, irradiate the surface, all sorts of things. So you may need to actually have extra protection like magnetic fields or extra ozone or thicker atmosphere to absorb some of the radiation in order to counterbalance some of those. One of the things though is that after time, we still think all M dwarfs quiet down. They get probably to kind of sun level quiet. So if you just wait long enough, all M dwarfs probably still could be habitable, that lots of those magnetic activity things don't matter anymore once you get, certainly for the most massive M dwarfs, which is almost an oxymoron, you know, it's a few billion years, couple of a few billion years, and even for the smallest stars in our galaxy, it's probably still only 7, 8, maybe at most 9 billion years, which sounds like a long time, but when you're a star that's going to last for 1 trillion years, waiting 9 billion years to set up habitable life or, you know, a habitable world is not a very long time. But it's a great question because it just makes us probably have to rethink really what true habitability is in terms of stellar activity, but also in terms of where other places you could have liquid water. I mean, there are places in our own solar system like Europa, which is a moon of Jupiter, and Enceladus, which is a moon or satellite of Saturn, which there's good evidence that they have liquid water beneath their icy surface, even though they're at 5 astronomical units and 9 astronomical units away respectively. They should be frozen solid, and yet there's liquid water. There probably are places that life could easily exist, and so those would not be considered habitable in kind of the classic way that we define habitability, but they really are. And so we have to be a little more careful probably in thinking about what true habitability is.
So there's a few other spin-off questions.
Yeah.
That says, if so, what implications do you see for finding truly Earth-like worlds in M dwarf systems, which you kind of answered a little bit?
Yeah, I think there's still a high possibility. I mean, I think there's now pretty good evidence that you know, there are several small worlds, at least several planets around almost every star, and that around the M dwarfs, those are preferentially small rocky worlds. And so when you add up all the billions of, you know, small stars and small planets in the galaxy, I think you're bound to find ones that have similar conditions to what we have on Earth. You know, it doesn't necessarily mean we're going to have life and all those other things because we don't know exactly how that gets set up yet. But certainly to find a world that has the right temperature and conditions and water and all of those things, you know, although we have no direct evidence for the abundance of other Earths out there, I do think that's probably quite common.
So the last little question from this question is, should we still be optimistic, or do we need to develop better technology for finding Earth-like worlds around sun-like stars?
Oh, we should still be optimistic. I mean, we should still look for, I think the answer is yes and yes. We should still be optimistic, but we should also still develop new technology for looking for planets around all types of stars, including sun-like stars, or ones that are maybe even more massive, or some that are a little less massive. There's actually a whole class of stars between G stars like the Sun and M stars, like the K dwarfs, which may actually also be a sweet spot for finding habitable worlds because they're they live a little longer than G dwarfs. They're not as active as M dwarfs. They're more abundant than G dwarfs. So that we may be missing a whole thing in the middle that that we've missed so far. So yeah, I think the answer is, I think, still be optimistic. Remember, there are 70% of all the stars in the galaxy are M dwarfs. So if there are, let's say, 200 billion stars in the Milky Way, that's 140 billion M dwarfs. All right, each of which likely has a few planets around it. So that's a lot of planets. I mean, we're talking now hundreds of billions of planets, probably all small planets. It's bound with those odds to have even quite a number of them have kind of Earth-like conditions. I think we'd be naive and maybe arrogant to think otherwise.
So that's all the questions we have right now. If more people want to keep asking questions in the Google Hangout forum,
yeah, ask more questions in the Google Hangout. If you're on, I see several people are on right now, and if you're on right now, type in more questions. I don't think we've received any via email like we sometimes do, but I will check really quickly just to make sure. But I don't see any. One thing I'll say while we're kind of waiting to see if there's any updates or new questions is one of the really neat things about that we've learned so far from Pluto, and I'll probably say this again during the epilogue section, is from just the few images that we've seen so far, Pluto, which also should be a very dead world, probably made up of, it's probably mostly made up of kind of ice and a little bit of rock in the outer solar system. One of the cool things that we've seen is that it doesn't look very battered. You look at like a world like the Moon or Mercury, they're covered in craters. They're covered in all these pockmarks as things have like hit them over the billions and billions of years. And partly because those are also fairly dead worlds. They're not geologically active. They don't have lava. They don't have things like that that will recover them or resurface them. So it's probably not that Pluto hasn't been hit, but it looks like something is, acting on Pluto to kind of cover up the craters. And that means it's a young surface, and that means that in some way it has some mechanism for kind of covering up the craters. And that is unexpected because we don't really know of a good mechanism for a world that's that far away, that's not orbiting another giant world that might impose tides or something on it, of how it could actually still have some level of geologic activity. And so I think that will be an amazing mystery going forward, and I'm sure lots of clever people will come up with some interesting solutions.
So stay tuned for the epilogue.
So stay tuned for the epilogue. We'll see if we've learned more in a week.
Okay.
And if we haven't, it'll stay tuned for the rest of Science Changing.
So there's now another question from Brandon here. It says, could there possibly be one of these very dim, difficult to detect brown dwarfs very near our sun? Perhaps closer than Proxima Centauri, our closest star, at 4.2 light years.
Oh, cool. Another cool question. Yeah. So the answer is yes. There very well could be. And there's actually been kind of science fiction books about this. Isaac Asimov wrote a book called Nemesis, which was basically a small star, brown dwarf. It was actually a star in this case that was near to the sun. It was actually kind of orbiting the sun, or actually in this case it wasn't orbiting, but it was very near the sun, but it had been kind of shrouded by the dust of the galaxy for years, and was actually finally seen, and turns out it was really close. But of course, we could have something that's really small and dim and cool, that's actually pretty close. People have actually looked, and in recent years there was one that was discovered. It has someone's name. It was discovered by a professor at Penn State named Kevin Luhman, and it's called Luhman. I can't remember which number it has. He's discovered a number of objects, and they're called Luhman 1, 2, 3, 4, so on and so forth. But this object that he discovered is not. It's actually a little bit farther than Proxima Centauri, but it was an object that's fairly close to our kind of solar neighborhood, but had not been discovered because, just as Brandon's question implied, it is a very cool brown dwarf, and so just is not giving off very much light. And so it wasn't till just a few years ago where we actually found this object. And so there certainly could be several more of those around. Myself and a friend, my friend Dr. John Bachansky, who's now a professor at Rider University, we actually spent a little bit of time when we were across the river at MIT thinking about if we could actually find nemesis worlds, that's what we called them, after the Isaac Asimov book. So we spent a little bit of time looking. We didn't find anything, but we did actually spend a little bit of time seeing if we could find really nearby undiscovered stars.
Another question that just came in. Back to the habitability of M dwarfs. Supposedly planets around them are tidally locked with their stars. How would that affect life according to you? Life only on one side of the planet, or at the edges towards the night side, or on the night side?
Oh, good question. Yeah. So if you had, remember that around an M dwarf, the planet has to be much closer to be habitable. So because the M dwarf's giving off less light and less energy, you actually have to have a planet much closer so that if it wants to have liquid water on the surface. And so because of this, the tides from the star can actually be so strong that it doesn't let the planet rotate, just like our moon, right? Our moon doesn't actually rotate. We always see the same side of the moon, and that's because the tides from the Earth are so strong that it's actually kind of stretching the moon, and as the moon tries to rotate, it's not allowed to. And so that happens probably to planets in the habitable zones of at least the smallest M dwarfs. So in terms of how you would set up life on those, because you'd have one side that was always hot and you'd have one side that was basically always cool. Some of that could be mitigated with atmosphere. So if you had a thick atmosphere on the world, the atmosphere can actually transfer heat around. So you get these big circulation patterns like we do on Earth, get weather, essentially. And the weather can actually take heat from the day side and transfer it to the night side. And so you actually would get some, if you had nice, like, thick atmosphere with weather, you actually might get some patterns setting up to redistribute some of the heat from the day side to the night side. But I could imagine some scenario, maybe there's some science fiction books about this, where you maybe set up, some kind of civilization right at the boundary of the day-night side, and when it was time to sleep, you would, commute across to the night side, and you'd go to bed. And then during the day, maybe you'd come across the day side and you'd work near the day side where it wasn't too hot, but where it was nice and light. I don't know. I can imagine some scenario where, like, again, a intelligent species or even just an evolving species would figure out a way to kind of go back and forth between day and night very easily to help regulate temperature, but also be able to, like, work effectively. But that's a really cool question. I don't think actually that probably inhibits life. My guess is if life is going to happen, it's going to be able to overcome something like that.
It can evolve to prefer day or prefer night.
That's right. So as Aurora just said, yeah, it could evolve to really just like the night or like the day. I mean, again, we'll talk about this a little bit in Module 9, but everywhere we look on Earth, there's life. Even in places that you would think there shouldn't be life, the driest deserts, the saltiest oceans, the coldest places, the hottest places, everywhere we look, there's life. And so, at least on Earth, or one example, a place where life has set up, you actually really get it being abundant and resilient.
Cool. Brandon just wrote another comment, but I can read it out loud still. The author, Isaac Asimov, called these planets ribbon worlds. This is directed at the previous question.
Oh, cool.
Because the ribbon between light and dark was potentially habitable. He wrote a novel called Foundation and Empire, which had a ribbon world called Radol.
Perfect. Well, thank you, Brandon, for that answer. So this is why Brandon was such an amazing piece of this class. So actually, a lot of the assessments that you guys have been doing were created by Brandon, and we're modifying them as we go through, changing some of the math, maybe adding a few more, taking out some. But Brandon really gets the majority of the credit for creating them. And actually, when we get to the final exam, which Brandon completely wrote, which is just really beautiful and it's really fun. So I hope you all are looking forward to taking the final exam in a few weeks when we get there. It's a real amazing work of creativity and pedagogy. So thank you, Brandon, for that answer.
Awesome.
Good.
Cool.
We've got 5 more minutes. So if there's any last questions, feel free to send them in. Is there anything more? Did it post anything to the discussion forum?
Nope.
Nope.
Nothing more in the discussion forum. We
Okay.
can wait a few minutes.
Yeah,
see if anybody posts.
We'll wait a few minutes and see if people. I'm looking to see. Oh, it looks like maybe I got something here. Let's see. New comment. I did get one. Let's see. It says, are you familiar with measuring the composition of stardust grains by methods such as mass spectroscopy, looking for their anomalous isotopic signatures of nitrogen, carbon, silicon, yielding information, about, that's where my thing cuts out.
Is it?
It's on my YouTube.
It's on YouTube?
Yeah. Yeah, I got it. Do you see it, the rest of the question, Aurora? Mine cut off. Well, let me start while Aurora's looking for the end of the question. So yes, I am actually. I mean, one of the ways that we can actually get dust grains is actually one of the first ways that did. I mean, grains from outer space are actually falling on the planet all of the time. Actually, tons of material every day hits the surface of the Earth. And one of the first ways this was done was actually putting little, almost like Scotch tape, 2-sided tape on the airplane wings, and big jets, especially like the spy planes and things that flew at really high altitudes. And then actually the dust from outer space would rain down on the wings of these planes, and it would stick to the tape. And then when the plane landed, you could peel off the tape, and there you got your dust particles. One of my professors in graduate school, Don Brownlee, actually was one of the pioneers of this, and those particles are actually called Brownlee particles now. But there have been actually missions. One of the NASA missions that was very successful, the few sample return missions, a mission to actually go out somewhere and come back, it actually flew behind a comet, and it actually opened up a little piece of the spacecraft and collected dust that was coming off the back of the comet, and then it closed back down, then actually came back to Earth, and it landed. It was actually caught kind of by a helicopter as it was landing, so it wouldn't crash down to the surface. And then they've been actually studying those little dust particles. So, and they use all sorts of things from mass spectrometers to electron microscopes to actually study these tiny, some of them are microscopic dust grains that are kind of raining down on the Earth. Did you see the end of the rest of the question?
Yeah. Do you want me to read the whole thing?
Yeah, let's read the whole thing.
Are you familiar with measuring the composition of stardust grains by methods such as mass spectroscopy, looking for their anomalous isotopic signatures of NCSI, yielding information about stellar evolution and nucleosynthesis? It is amazing that we can detect these tiny signatures.
It is amazing, and yeah, and it's something that's happening kind of all the time now. It's amazing what we can do from tiny little particles, or to be honest, I find it still spectacular that we can look out into distant space, and by using the basic principle of spectroscopy, which all of you have learned about in this class, we can actually tell things like the compositions of stars and planets and galaxies by just using kind of like tricks of light and a little bit of interesting physics. We can learn a lot about the universe, even at great distances. So yes, I find all of that still very cool.
Cool. So that's it for now. Do you want to wait another minute? It's
Yeah,
10:59.
We'll wait 1 minute to give the full hour, but we'll have one more office hour for this class oh, looks like there's one more maybe. Is there another? Oh, no, it's just Stephen who was giving the end of his question. We'll have one more office hour in 2 weeks. That will be the last office hour. We have a couple more modules to release. And then, as we said, we're going to be doing shooting an epilogue, kind of an update, like the things that have changed in Alien Worlds since we actually shot this class for the first time last year. And then there'll be a final exam and the class will be done. So thank you for joining us, either live with some of your questions, or if you're watching this later today or in the next couple days. And we'll see you in a couple of weeks, and I'm sure you'll hear from us again with course updates, with video emails. Keep the questions coming and stay curious. All right, take care.